So it's my pleasure to introduce the speaker today. Olivier Wittenberg will speak on the cycle class map for zero cycles for local fields.
Thank you very much. So thank you for the introduction and for the invitation to speak in this seminar. So everything I'm going to say today is joint work with the I'm sorry. Okay, I'm sorry. So everything I'm going to say is joint work with NNNO. So the goal will be to explain some new results we obtained about Chow groups of zero cycles for surfaces over local fields and strictly local fields. So local fields is the usual sense of the word. Strictly local means, for example, the maximal and ramified extension of a p-adic field. So especially these will be results about surfaces with positive geometric genus. And this will be the point, as I will explain, but let me start by setting up some notation for the whole of the talk. So capital X will be a smooth projective variety over a field K, capital K. And as usual, I will denote the Chow group of zero cycles by CH0 of X. So recall this is the group of cycles, so free group on the closed points modulo rational equivalence. So rational equivalence is generated by linear equivalence on the curves lying on X. Because X is projective, there is a degree map. And I will denote the kernel by A naught of X. Okay.
So just 1 second, we check for the sound. On peut pas enlever le micro parce que ça fait beaucoup de bruit. Vous ne pouvez pas récupérer le son directement? Ah, ok. Je peux remettre le micro d'achat. Oui. Et donc il enlève le sien, c'est ça? Je baisse le sien alors. Oui. Ok. Yeah.
Okay, so recall. So in dimension 1, this is nothing but the Picard group.
Yes, the shift, François.
Okay, thank you. This is just the Picard group, and if there is a rational point, then the degree zero part is nothing but the set of rational points of the Jacobian variety. So this group in dimension 1 is very well understood. Now in dimension greater than 1,
you mean geometrically connected X?
Yes, okay. Geometrically reducible for the whole of the talk. So in dimension greater than 1, this is one of the simplest invariants that one can associate to X. But it's in many cases it's very difficult to determine the structure of this group or to compute it in any given example if X has dimension greater than 1. And this even over an algebraically closed field. So to illustrate this, let me recall the situation for surfaces over the complex numbers. Well, we have a conjecture, box conjecture. So in dimension 1 here, you see that this group is the group of points of an abelian variety, so it's represented by an abelian variety, and in dimension greater than 1, say dimension 2, it's conjectured that this group A naught of X should be representable in a suitable sense by the points of some variety, if and only if H2 of X of X is 0. So what is known is that if you have so this is the geometric genus, and what is known is that if you have a surface with non-zero geometric genus, then this group is huge. It's not representable in any sense. And this conjecture in the other direction is out of reach. Okay, however, there is one simple thing that one can say over the complex numbers and more generally over algebraically closed fields in any dimension is the fact that this root is divisible. In the case of curves, it's clear from the above description, and in general you can reduce to the case of curves by finding curves lying on X going through specified points. Okay, so this is the situation of the complex numbers. So, there is one situation in which this group is well understood. It's when the field is a finite field. So when K is a finite field at Q, then everything is understood because of higher dimensional class field theory. So let me recall the relevant theorem, which is due to Kato and Shuji Saito, 1983. So in this case, the Chow group of zero cycles of degree 0 is always finite. But it's more precise than this. One can in fact compute it in examples. It's very controlled. So namely, there is a map, a natural map going from the Chow group of zero cycles to the abelianized fundamental group defined by Frobenius substitutions. You send a close point to the class of the corresponding Frobenius. And Kato and Saito proved that this map is injective. So to detect rational equivalence, you just need to compute the image in this group. And the image of this injection is very well understood. It was determined by Lang. So this gives complete control over this group. And for example, if the variety is simply connected, from this you can deduce that the Chow group of zero cycles of degree 0 is trivial.
So the image are just the elements whose degree is integer.
Yes, exactly.
Okay.
Okay. So, but it's really the only situation where one has a complete hold on this group. So from now on, I will consider local and strictly local fields. So capital K will be the quotient field of R. R will be a Hanselian discrete valuation ring. The residue field is K, small k. For simplicity, I will assume that capital K has characteristic 0, but it's really not an important assumption. And we'll let P denote the characteristic of small k, which may be 0. And so I will consider the two cases when small k is finite or separably closed. So capital K local is when small k is finite, and capital K strictly local when small k is separably closed. So in this situation, examples of course are p-adic fields here, QP and finite extensions. And here, for strictly local, there are two natural examples: the maximal and ramified extension of the p-adic field, but also C double parenthesis T is an interesting example. So in this situation, one has a good structure theorem for the Chow group of zero cycles of degree 0, which was proved by Saito and Sato.
By the way, when you consider the unramified extension, you can consider it either algebraically or complete, and I guess there is a general rigidity fact that it doesn't matter.
Yes. It's true. Yeah, I only assume Henselian
Yes.
can apply everything to both cases. So, okay, so the structure theorem by Saito and Sato in 2010. So here the field has infinite transcendence degree, so you cannot avoid a big divisible subgroup just as in the complex case. But the theorem tells you that apart from this, there's just a finite group, at least prime to P. So precisely, you can write A naught of x as D plus F, where F is finite over order prime to P, and D is a group which is divisible prime to P. So this means D mod ND equals 0 for n prime to P.
So if P is 0, you don't say prime to P. You just,
Right, so if P is 0, it's divisible plus finite.
Yes. Because prime to 0 is not.
Yeah, okay, yeah, I agree. Okay, so, right. So, as I mentioned, so D is a bit analogous to the group over the complex numbers. As you've seen, it's extremely hard to understand. So here it's probably even harder. So, I mean, there's really little known about it. It's only known that D can contain torsion, even for simply connected varieties. So this is due to Asakura and Saito. But in this talk, we will focus on the finite group F, which is really analogous to the group over finite fields here. So, in this sense, this theorem is analogous to the theorem of Kato and Saito, which says that over finite fields, the group is finite. Now, one would like to have an analog for the second part of the theorem too, which allows you to compute it in examples, or to get a hold on its structure. So, for this, so we want to study F. F is finite over prime to P, so we fix a prime L, different from P, and we look at the L primary torsion of F. And the general tool to study classes of cycles is the cycle class map to étale cohomology. So when you consider the cycle class map psi, which goes to CH0 of x, so if D is the dimension of the variety, goes to H2D étale x ZLD. So here you
What is going on?
can you still hear me?
Yes. François?
Oui, quelqu'un essaie d'appeler la salle, alors...
Qui appelle ça?
C'est quelqu'un qui essaie d'appeler depuis l'extérieur, je sais pas
Ah bon?
Okay, so I go on.
Il va s'arrêter tout seul.
J'espère.
Okay, so we consider.
Okay, so just for Beijing and Tokyo, someone is calling the room, so we don't know who is. We will continue. Okay.
Okay, so we consider integral LRD cohomology. So this is a finitely generated ZL module. So because of this, any element which is infinitely divisible here must die in there. So this map kills D. So only F survives. And well, another way to phrase this is to consider this group tensor hat ZL, where tensor hat means you consider the inverse limit of CH0 of x modulo L to the n CH0 of x. So this kills the divisible part. And really the analogous question to the theorem over finite fields is this map injective? So what about the injectivity? Oh, sorry. So in fact, over a finite field, if you consider this over a finite field, you really get exactly the map here, Frobenius substitution. You can identify this cohomology group, for a fixed L with the pro L part of pi 1 L. So really it's a generalization. Okay, and if you can answer, when there is a positive answer, then you can hope to compute F by computing just its image in étale cohomology. So this question has received a lot of attention from the 70s to the 90s after initial work by Bloch, who initiated a method for studying cycles, torsion cycles, using K-theory. And by combining this and the Bloch-August theory and the Markovitch-Suslin theorem, it was recognized that one could get a good hold of codimension 2 cycles on arbitrary varieties, on varieties of arbitrary dimension. So there are many names here to mention. So Polyethylene, Sansuc, Soulet, of course, Kato and Saito, which I've already mentioned, and also Saito himself. So wrote a whole series of papers about this problem using K-theory for cycles of codimension 2, so for surfaces for 0 cycles. And quite generally, these methods produced very effective results for rational surfaces and more generally for surfaces with geometric genus 0. So an example of a theorem obtained in this series, which I think should be attributed, I should mention, Raskin. So this theorem should be attributed to Polyethylene and Raskin, 1985. So about this question, in the strictly local case, capital K, strictly local, yes, maybe I did not stress this enough. The theorem of Saito and Sato is for both cases, local and strictly local. So here, if K is strictly local and X is a surface with geometric genus 0, then there is a positive answer. Then psi is injective. So the goal of the talk will be to try to answer, to give some answers to this question for surfaces with non-zero positive, with non-zero geometric genus. So over local fields and over strictly local fields. So actually the strongest results will be about local fields, but I also hope to show that the situation is perhaps unexpectedly very different between local fields and strictly local fields. Okay, so maybe I start here. So the first theorem I want to mention is about strictly local fields. And actually over C double parenthesis C. So if you want to consider surfaces with non-zero geometric genus, the first class of surfaces you look at is K3 surfaces. And in this respect, we can prove the following. So if X is a K3 surface over C double parentheses T with semi-stable reduction. Then the answer is positive. So what does it mean? The cycle class map is injective, but here, so we're in the strictly local situation, so it's a field of cohomological dimension 1, and you can try to understand what this cohomology group is in this case. And because the surface is simply connected, it really means that there's no F. In other words, the Chow group of 0 cycles of degree 0 is divisible. Okay, so let me explain the strategy for the proof of this. So we will consider a model over the ring R. So here R is C double bracket T. And I will consider script X over R, with projective regular model. Let me denote the special fiber by A. And its irreducible components by AI. So since we're in a semi-stable case, A here is reduced, and I will assume in addition that it's a simple normal crossings divisor on X.
So this is not needed or in the result, or?
I mean, you can always choose a model like this. I mean, we work over C double parentheses T.
Yes.
So, I mean, I'm explaining the strategy for the proof, so we choose such a model. Okay?
No, but if you have a model without simple normal crossing,
Yes.
then
You mean if it's still semi-stable in this weaker sense?
yeah.
Yes, okay, yeah, you're right. The theorem holds with semi-stable in the weaker sense. That's what's written in the paper, but I focus on this for simplicity. Okay, so, yeah. Okay, you're right. I mean, there's an ambiguity in semi-stable. So, in this situation, okay, let me use a new ball.
And you need that the total space is regular, so it's not enough to have a log smooth
Right.
semi-stable.
Right. So in this situation, we consider the cycle class map psi. So CH0 of x tensor half ZL maps to H4 x ZL2. And we consider what happens on the model. So on the model, we have one cycles on the model. And the cycle class map to Étale cohomology of the model. Now vertically, you can write localization exact sequences. You can restrict to the generic fiber. And before that, you have one cycle on the special fiber. And here you have cohomology with support in the special fiber. there's a cycle class map again, which we'll call Psi1A. So 1 cycles on the special fiber. Okay, and now the point is that Saito and Sato did not only prove the finiteness theorem here, in fact, they proved something much stronger, which underlies this theorem. They proved that the cycle class map for 1 cycles on the model is an isomorphism. Okay, so this is Saito and Sato. And they proved this in the generality of their theorem, arbitrary dimension, local or strictly local field.
But there they don't have regular model.
Yes.
They have regular model.
They assume they have one. Yeah. They assume they start with one, and then they claim, oh, you mean to prove this? Okay, but to prove this, you can reduce to the, I mean, using
Okay.
your improvement of the Young theorem. Yeah. Okay, so now if you look at this, and there's one point here which is 0 cycles extend to 1 cycles on the model, so this map is surjective. If you look at this, you see that you want to prove that the bottom map is injective. Of course, it would be enough for the top map to be surjective. But in fact, it's never the case for the generations of K3 surfaces. One can check that this is never the case. The top map is never surjective. So one has to be more precise. But still, it's possible by looking at this diagram and using this isomorphism to translate the injectivity of the bottom map purely in terms of the special fiber. So I'm just giving you the results. It's really reformulation using the isomorphism. So that's really step 1. So from this, you deduce that this group is divisible if and only if a certain complex is exact. So this is a translation you can do in general, but for simplicity, let me use some very simple properties which come from the fact that I'm looking at a K3 surface to give you the translation. So here we find that a certain complex should be exact. So let me write it. Q mod z equals to Q mod z to the power I. So direct sum of I copies of Q mod z. And then it goes to the direct sum of the Néron-Severi groups of the components tensor Q mod z. So if this complex is exact, that's the property. Okay, what are the maps? Here, it's just the diagonal map. And here, well, if the dimension was 1, it would be the intersection matrix. So in general, it sends, if you take lambda on the jth component, it's sent to, if you go to the ith factor, you look at the class of AI intersection AJ tensor lambda on the ith factor for I different from j. If I equals j, you can anyway modify by an element coming from the left to determine the image. So this describes the map. Okay, so this is a concrete criterion which you now have to check. So now that's the second part of the strategy.
Is exact in the middle, you mean?
Yes, exactly. Yeah, just this. So now you have transformed the problem into something which is purely on the special fiber. It's completely concrete. So then you have to use the fact that special fibers of the generations of semi-stable K3 surfaces have been classified. So there's a whole literature about this, starting from the work of Kulikov, Persson, Pinkham, and Miranda and Morrison in the 70s, the 80s. Morrison. So they classified semi-stable degenerations. Of K3 surfaces. So here, one would have to be precise. It means that if you have a semi-stable K3 surface, they give you some nice model for which they can tell you what the special fiber is. And so there is a classification. And if you use this, and if you know enough about the surfaces AI which appear here, and which in this classification are rational surfaces or ruled surfaces, except in the case of good reduction, then using these two things, you can translate the problem into a combinatorial one. So you obtain a combinatorial problem. So namely, so it's about the combinatorics of the special fiber. Namely, the biggest case of the classification tells you that so in many cases you have a K3 surface which degenerates to rational surfaces in such a way that the dual complex triangulates a sphere. So then you obtain questions about triangulations of the sphere, and in fact negatively curved triangulations of the sphere. These questions are in fact hard in general. I mean, these objects are hard in general from a combinatorial point of view, but it turns out that for this particular problem, you can solve it. So that's the last part. Solve it. And I'm sweeping lots of details under the rug. I should mention that these degenerations are not algebraic. It's only in the analytic category. You don't get schemes. So you have to work a bit to glue the pieces together, but it can be done.
What do you mean you don't get scheme? Do you get algebraic spaces, or you get...
So I think you get algebraic spaces, but it's not written in the literature. So they use analytic manifolds.
And in your results that you mentioned, you always say projective. So
Yes.
do the results hold, the proof use projective, or for example, the proof of Kato and Saito use projective,
Yes,
or
I mean, it's
not proper? Or?
in many places you use hydroplane sections. And you use Bertini theorems and things like that. So
So even in the last thing about the generation of K3, you really need projective.
no, I mean
no.
you need Bertini theorems to prove, for example, this isomorphism. But once you have it and you have translated the question in this form, then I mean you just look at this complex and you forget everything else, and now you can lose projectiveness.
But the classification that they have
Yes.
for analytic degeneration will apply in particular to the projective ones.
Yes.
So it,
But they give you no. But what they say is if you start with a K3 surface, then there is a model which is regular, and such that the total space is regular and the canonical divisor on the total space is trivial. But this is not a projective scheme. This is only an analytic manifold. I mean, to get the condition that K is trivial on the total space. And this is what you need to analyze the special fiber.
and then you have to go from this to your model.
Yes, so you have to use weak factorization and things like that. You use weak factorization and check that the complex doesn't change and so on.
And what about ramifying the original local field? Does it change the problem or not?
Sure, yeah, you lose the question. I mean, it's a question about a finite group, I mean,
Okay.
F, so you lose everything.
Okay.
Okay, so that's about proof of theorem 1. So a few comments. So first comment is that the first step of the strategy here is completely general. You can draw this diagram in any dimension, and you can always translate the injectivity of psi as the exactness of the certain complex which looks like this, except it's a bit more complicated in general, and in particular, if X is not simply connected, then it's not true, or at least not clear at all, that it only depends on the special fiber. Okay, the second comment is that if we had the results of Kulikov, Persson, Pinkham, Miranda, Morrison in mixed characteristic, then the whole proof would go through over, say, the maximal unramified extension of QP, and you would get in the same way that the group F is trivial, which means here that A naught of X is prime to P divisible.
You
But-
said that they work analytically, but then they must use not formal series but convergent series, otherwise it doesn't make
Sure,
sense.
sure. So the first, indeed, the first step is to reduce from C double parenthesis T to convergent
Okay.
series. I mean, I'm skipping details on that. So, okay, so again, if we had these classification results in mixed characteristic, we would get prime to P divisibility over QP and R. And the third comment is that for K3 surfaces which are not semi-stable, we don't know. I mean, it's an open question for us. We don't know what happens. The only reason why we need semi-stability is that it's only for semi-stable K3s that there is a classification. Okay, so now I turn to local fields.
And in their model you said that they have the total space regular, but is it with reduced fiber or not?
Yes, they always work with reduced fibers. Yes.
But what do they have to assume to get it? Some. You said that it's not always the case that there is such, or they show that there is such, or
No, they show that there is such, but it's not always a scheme.
with reduced special.
Yes, yes.
Ah. Oh, okay.
I mean, you start with the assumption that it's semi-stable as a scheme. You assume to start with that X has semi-stable reduction as a scheme, and then they tell you can find another model, which is maybe not a scheme, which is still semi-stable, and for which K is trivial.
Ah, okay, this is the point.
Je pense qu'il vaut mieux laisser partir.
Ah, il
voir
part tout
l'autre,
seul.
ouais, et descendre l'autre.
Okay, so I turn to local fields. Now K is a local field. And so I will state a theorem. So as you will see, this will be a much stronger theorem than this one. So I guess it's the main theorem of the talk. It's also about surfaces. And I will again work with the model. So this time I assume that I have one like this. So I keep the notation X, a regular projective model. Again, A is the special fiber. So I keep all of the notation. And I assume, so maybe there are multiplicities now. I'm not assuming semi-stability, but I assume that A red is a simple normal crossings divisor. Okay, so then theorem 2. So you have to make two assumptions. So the first assumption is about the AIs. So the AIs are smooth projective surfaces over a finite field, and I assume that they satisfy the Tate conjecture. And the second assumption has to do with the Albanese variety of X. So I assume that Alb X has potentially good reduction. Of course, this is the case, for example, if X is simply connected. Okay. And then, so the theorem is that again, psi is injective. So the cycle map to H4ZL2 is injective for any L different from P. So we get a positive answer in this situation. So again, this was known for surfaces with geometric genus 0. It was proved by Shuji Saito in the 90s. And the point is that it applies to surfaces with non-zero geometric genus, and as I mentioned, these are those for which, over the complex numbers, the Chow group is not representable. So a few remarks. Okay, first remark about the Tate conjecture. Here we assume it for the components of the special fiber, but it's very often the case that it's satisfied for trivial reasons. So there are many, for example, there are many P3 surfaces, P3 surfaces X, for which you have a model, and the special fiber is the union of rational surfaces or ruled surfaces, such that AI is birationally ruled for each I, and in this case AI satisfies the Tate conjecture trivially. So there are many examples where this can be applied. Second remark is that the conclusion can be formulated in an equivalent way, which also appears in the literature. So equivalently, so there's a natural pairing between the Chow group and the Brouwer group. You evaluate classes of the Brouwer group at points, and you take the local invariant of a class field theory, and so this goes to Q mod Z. And the conclusion is equivalent to saying that the left kernel here is divisible by L. So this can be seen as a higher dimensional generalization of Lichtenbaum-Tate duality. Lichtenbaum-Tate duality says that for curves, this is a perfect pairing on both sides. And clearly, the maximal divisible subgroup has to be in the kernel because the Brouwer group distortion. Okay, and the third remark is about the other assumption about the Albanese. So in fact, if you remove it, then the theorem is wrong. So there are counterexamples due to Parimala and Suresh in the 90s. So theorem wrong without assumptions, without any assumption. On the Albanese. So you have to put some assumptions. Okay, so in principle, this should apply to all simply connected surfaces. So now I will explain what the ingredients of the proof are. So ingredients of the proof. So you start in the same way as for theorem 1. You write. You look at the diagram on the top. you write the cycle class map for one cycles on the model and on the special fiber, and you use the theorem of Saito and Sato that the map in the middle is injective, it's an isomorphism, sorry. But then, here in this situation, we will actually prove that the map on the top is surjective. So here, so we'll prove surjectivity of psi 1a. So from CH1a tensor head ZL to homology with support. So really that's étale homology H4a x ZL2. So again, by the theorem of Saito and Sato, this is enough. But it's perhaps unexpectedly strong. I mean, in theorem 1, this was not true, but okay, here that's what we prove. Okay, so we start by reformulating this a bit as we did in theorem 1. So the first thing is psi 1a is surjective if and only if. So here again you dualize, and so you write the dual of these groups by combining Poincare duality and the duality for the Galois homology of the ground field. So you find that the dual of this group is H3. So let me write here H3 of A QL mod ZL1. And then you consider the following map. First of all, you go to the direct sum over each component. And then you mod out by a certain subgroup. So the same group on the top. And I mod out by a certain subgroup which I denote CH1AI orthogonal. And I will define this group in a minute. But the condition is that the composition here is injective. Okay, this map here is injective. So this is a purely formal reformulation, and the group, I'm sorry if I mentioned what it is, it's just the group of those classes which die when you restrict them to curves. So the set of classes alpha in H3 AI QL mod ZL1 such that the restriction of alpha to any curve is 0. Okay, so then I will explain how the various hypotheses play a role and how you prove this. I mean, I will just give a picture. Okay, the first thing is this. You have to use the hypothesis on the Albanese. So the Albanese is related to H1 of X of the geometric generic fiber, and because X is a surface, it's related to H3 by duality. Okay, now if you use this, you can try to relate this H3 of the generic geometric fiber to what happens on the special fiber using the results of Rappaport and Zink. To prove the monodromy weight conjecture for surfaces in mixed characteristic. So here, okay, you have to argue, I'm not doing it, but these two ingredients will allow you to conclude that H3 of A bar, so bar means you go to an algebraic closure, QL is pure of weight 3. you look at the weights of the action of Frobenius on this, and because A bar is proper, but maybe not smooth, a priori it has the weights 3 and possibly lower. But in fact, using this hypothesis, you find that it's pure of weight 3. And because it's pure of weight 3, it has to inject into the direct sum of the same groups over the components. This is because you can write what the kernel is, and you find that the kernel is pure of weight. I'm sorry, maybe not pure, but it's. I mean, there's no weight 3 in the kernel. Okay, so that's one point. Then, the second point is to use the Tate conjecture in not in an essential way, but okay, it's a fact that the Tate conjecture implies that the action of Frobenius on the H2 of AI bar is semi-simple for the eigenvalue 1. So, I mean, sorry. Yeah, it's partially, so let me say it's partially semi-simple. So this is a classical fact. And if you use this semi-simplicity plus some weight arguments, from this, you can deduce that H1 of the finite field with values in H2 of A bar QL of 1 injects into the direct sum of the same groups over the components.
What is partially semi-simple?
I'm sorry?
What is partially?
So it means just for the eigenvalue 1, it's semi-simple for the eigenvalue 1.
This is part of the Tate conjecture.
Yeah, I mean it's a consequence of it.
Okay, in terms of numerical.
Okay, now putting these two things together, you deduce that H3 of A, the Austrian self-spectral sequence, H3 of A QL1 injects into the direct sum of the same groups over the components. And now there's a bit of a miracle that you can deduce from this the same thing with torsion coefficients. H3 of A QL mod ZL of 1 injects into the same thing. And the proof here is very simple. I mean, there's nothing deep. But it uses crucially the fact that we're looking at surfaces. And it's the only place where it's really crucial. You have to use some Lyell-Vettori spectral sequence, and you want some groups to be torsion-free, and well, it works in dimension 2 and not in a higher dimension. Okay, so you're almost done. You've proved that the first map here is injective, but the second map is no problem at all. That's where we use the Tate conjecture. So in fact, the Tate conjecture here implies that these groups CH1 of AI orthogonal are 0. So if you put all of this together, you're done. Okay, so that's how the proof looks. So a few comments. First of all, it applies, so as I mentioned, to K3 surfaces, even in the non-semi-stable case. And also in the semi-stable case, as you see, there is no need for any classification results. In a sense, it's much easier. There's no combinatorics involved.
But you assume that it is strict normal crossing, while before you did not assume.
You're right. You're right. But I mean, conjecturally, but I did not assume that the multiplicities were 1. Okay, so that's one point, and in particular, so this. So you see, if we had the classification in mixed characteristic, we would get the injectivity for K3 surfaces over the maximal and ramified extension of a p-adic field. Now, this theorem gives it for free, assuming Tate conjecture and existence of models for K3 surfaces over p-adic fields. But it's a bit strange that if you want to prove the same results for the maximal and ramified extension, then apparently you need very strong geometric results. Okay, and I want to finish by coming back to strictly local fields.
Can I ask a question?
Yes.
Please.
Yeah. So you don't assume that closed fiber is reduced, but you said you use weight spectral sequence. What does this mean?
So I mean, so the point is to use the local invariant cycle theorem, which tells you that hi of a say a bar 12 surjects onto hi of x bar 12 invariance under the inertial group. But to prove this, you can reduce by using the Gabor-de Jong alterations. You can reduce to the semi-stable case. Okay.
Yeah. Thank you.
Okay, so I want to come back to strictly local fields. Okay, so we have a positive answer for p-adic fields, at least for simply connected surfaces. We have a positive answer for p-adic fields, assuming Tate conjecture. And for strictly local fields, we have a positive answer for surfaces with geometric genus 0. And then also for K3 surfaces. So what happens in general? Well, so we were quite surprised to find a counterexample in general. So that's theorem 3. And this works over both types of strictly local fields. So there exists X, a simply connected smooth projective surface over C double parenthesis T, such that, so again, what is the cycle map here? We're in the strictly local case, so the cohomology group H2D only contains information about the degree and the pi 1, abelian pi 1, but because it's simply connected, there's really nothing else than the degree. So here, a counterexample is an example where the group is not divisible. And here, we have A naught of x mod 2 is Z mod 2. So psi is not injective. And also, so that's one point. Another point is the same over the maximal unramified extension and ramified extension of a p-adic field for infinitely many primes p. So in particular, this shows that the hope for an analog of the Kato-Saito theorem, which was about finite fields, you could hope for an analog over this field, which is quasi-finite. This hope does not hold. I mean, the abelian fundamental group does not control the finite quotient of A naught of x by its maximal divisible subgroup. And another thing which I think, well, for me it was really unexpected, is that, I mean, you also get examples over strictly local fields like this. Now, if you take such an example, well, it's a surface, it's defined over some p-adic field. So if you take this example, you can apply to it theorem 2. So what you get in the end is a surface over a p-adic field for which the cycle map is injective, and the same, and in this example the Tate conjecture is satisfied, so that's okay. And the same over any finite extension of the p-adic field, you can, or at least any finite unramified, because then you see that the Tate conjecture is still satisfied. You can still apply theorem 2, but when you go to the limit, you get a counterexample. So I think that was a strange phenomenon. Okay, so there are many things that we don't understand. I mean, for p-adic fields, there's a rather complete result, except when the Albanese variety is non-trivial or does not have potentially good reduction, then we don't have a good answer, a good understanding of what happens. Also, over strictly local fields, we don't have. It would be good to have a better understanding of what goes on, what to expect, and also in higher dimension, I want to mention that most of what I've said works exactly in the same way in higher dimension, which could be interesting because the previous techniques were about codimension 2 cycles on varieties of any dimension. So the previous techniques do not say anything about 0 cycles in dimension 3 or more. So the only place where dimension 2 was really used is this one, and here we don't. I mean, we just don't know what happens. I mean, because of this problem, we don't know what happens in higher dimension. And an example of an open question, simple open question in higher dimension is this: if you take X, a smooth projective, rationally connected variety, over C level parentheses T, well, is the Chow group trivial? For such a variety, it's known that it has finite exponents, so trivial is equivalent to being divisible here. And okay, that's something we don't know in dimension greater than 2.
But you know it in dimension 2? Because it is rational, yeah.
Yes, it's rational, geometric genus 0. Well, that's it. Okay, so I'll stop here. Thank you very much.
Thank you. So, could we maybe start from Tokyo, Beijing, and then come back to Paris? Okay, so we start from Tokyo.
Okay.
In fact, we don't see you very well. There is no light.
Maybe. Yeah. So thank you very much. So in your last term, what are the numerical equivalent of this substitute? So for example, PG or bit number, second bit number.
So I'm not completely sure. I think the geometric genus is 3. I mean, I've computed this, but I've forgotten. It's Codera dimension 1. This I can tell you. I can tell you also the degeneration in this case is very simple. It degenerates into the union of 2 surfaces which meet along one curve. And each of these surfaces, I think, has geometric genus 1. The curve is an elliptic curve. And they have Codera dimension 1 too. Okay, I think that's all I can say.
So you just need the property of the bud fiber, or you no.
You mean to obtain this?
Yeah.
Yes, so actually, so thank you for the question. So in theorem 1, I wrote this complex on the top, which was equivalent to the divisibility of this group. So it's not correct in general. I was looking at K3 surfaces, but in general it's almost this. For a variety which is simply connected, it's exactly this, except that on the right you have to mod out by the same group as here, CH1 of AI orthogonal. But in the situation of K3 surfaces, this group was trivial. So yeah, so that's again a property of the special fiber, and so the exact property you need to get this example is a degeneration like this, such that the generic fiber is simply connected. This is very important. And the second property is that if you take the curve here, the intersection curve, say C, then you should have that the intersection number of C with any divisor in either surface is even, always even. for any I and any D divisor on AI. So that's what you need to do.
Thank you. Other further question? Yeah. Okay, so thank you very much for Tokyo.
Okay, so do we have some questions from Beijing?
Okay, so any questions? No? There's no questions from me.
Okay, so you have a question.
Yeah, you said something about, I did not register exactly, so about some passage to the limit for the strict analyzation of a periodic field. There was some comment that you made.
No, here at the end.
Yes.
No, so here I was saying that, so there is an example like this, over the maximal unramified extension of some p-adic field.
Yes.
Now the surface is defined over some p-adic field,
Yeah.
and to this surface over the p-adic field you can apply theorem 2.
Yes.
So you have this situation with the surface over a p-adic field, and on this p-adic field the cycle cost map is injective, and it's still injective if you go to any unramified extension, or maybe any finite extension if you believe the Tate conjecture. But if you go to the maximal unramified extension, it's not injective anymore. That's the counterexample here.
And so the point is the cohomology doesn't commute with
Right.
the limit.
Because it's ZL coefficients,
Okay.
not finite coefficients.
Okay.
But yeah, still it's maybe a bit unexpected. I don't know.
Other questions?
Well, I think that at some places you mentioned that you had to use Gaber's L prime alteration theorem.
Yes.
Could you give a specific example? Because here is not so convincing because you work with QL, so. The
Oh,
L
I'm
prime-
sorry, you're right. Here de Jong is enough. I'm sorry. No, you're right. No, it's really used just to prove the theorem of Saito and Sato, the isomorphism there, out there. Yeah. I mean, if you want to prove this, you can do any alteration of degree prime 12, and reduce in this case to. I mean,
you work with finite coefficient then?
Yeah, you're right. I'm sorry. Yeah, this theorem is true for finite coefficients, and that's how you prove it. Yes, thank you.
Other questions? So if not, let's thank the speaker again. And then we say goodbye to
Goodbye.
Regine and to
Yeah. No, it's not. Maybe I can.
yes. So we have
No.
still questions.
No,
Just,
I'm not. I did not.
yes.
Where is it used? So there was a question from Tokyo. So you said that you have this local monodromy theorem.
Yes.
So where does it enter in the?
So here, I mean, if you want to prove that H3 of A bar is pure of weight 3,
Yes.
so what you do is that, in fact, it's in an exact sequence, so it surjects onto H3. So you have this. Okay, but in fact, this is not the important part. The important part is what comes on the left. You have H3 of the model, say over the maximal unramified extension, with support in A bar. And so this local invariant cycle theorem allows you to prove, it's not completely obvious, but it allows you to prove that this is an exact sequence. It's exact here. It's not completely clear. But once you know it's an exact sequence, you're done, because this has weights at least 3. This has weights at most 3. So if it's not pure, it must be because of this. And this you can relate to the Albanese.
And Rappaport Sync assume that you have semi-stable.
Yes.
And you assume regular model, not?
Yes, you're right, but again, we can use alterations to prove the weight monodromy spectral conjecture. We can use alterations to prove it.
Okay.
Okay. Still other questions? So, if not, then we say goodbye.
Goodbye.